Good afternoon. My name is Costa and I'm here to present our paper entitled A Comprehensive Comparison of Voltage and Current Control Techniques for Three-Phase VSI Converters. This paper was made by Daniel Fernandes, Costa, Luís Barros, Delfim Pedrosa and Gabriel Pinto. The focus of this paper is to compare the performance of three control algorithms applied to VSI converters. Here is our agenda for this presentation. First, an introduction is given to power converters, with focus on VSI type converters, including their applications depending on the control used. Then, the control algorithms used to control the voltage or current of the VSI are presented. In the next topic, the simulation results obtained for voltage and current control VSI are presented. Finally, a comparison of the results obtained is made, and the conclusions obtained throughout this work are presented. Nowadays, electrical energy is indispensable for the execution of many tasks. With their increasing relevance, power electronic converters have become the focus of research to improve their performance and applicability. Power electronics converters can be grouped into four categories: DC-DC, AC-DC, DC-AC, AC-AC. Within each category, there are several topologies aimed at the most varied applications related to production, transport, and distribution of electrical energy, where are included power generation systems, power grid interfaces for alternative energy resources such as solar photovoltaic panels, wind turbines, and energy storage systems. Regarding the DC-AC power converters, these can be classified according to their power supply, being divided into two large groups: voltage source inverter, VSI, and current source inverter, CSI. The VSI topology is the most widely used, using a capacitor for the DC link. The VSI can be used in various applications such as AC motor adjustable speed drives or interfacing energy production systems from renewable sources with the power grid. Although they are widely used, there is a gap about control algorithms for VSI converters. VSI converters can be voltage control, where the converter generates the sinusoidal voltage responsible for feeding a set of loads in an isolated mode from the electrical grid. A diagram of a VSI using voltage control is presented in the first figure. Current control VSI converters are used in order to inject power into the electrical grid, as the second figure indicates. In this paper, three control algorithms are described and implemented: proportional integral (PI), proportional resonant (PR), and predictive model (MP). Starting with PI control, this control technique is based on calculation of the error between the reference voltage, Vref, and the voltage at the output of the converter, Vout. This error is multiplied by a proportional gain, Kp, and the integral gain, Ki. The resultant variable, V control, will be used as input for the SPWM technique responsible for synthesizing the signals applied to the semiconductors. To use this technique as a current control, it is only necessary to exchange the voltage signal for their current signals. The PR control uses the error between the reference voltage, Vref, and the output voltage of the converter, Vout, as in the PI control. The resultant sign, V error, is multiplied by a resonant gain, Ks, which will be input from a second-order integrator, SOG. The V error signal is also multiplied by a proportional gain, Kp, that will be summed with the output of the second-order integrator. The constant omega0 represents the fundamental frequency of the synthesized signal. For a 50 Hz application, this value is approximately 340 rad per second. To use this technique as a current control, it's only necessary to exchange the voltage signals for their current signals. Finally, the model predictive control is present. This control technique is based on the electrical model of the system, predicting the future behavior of the controlled variables, taking advantage of the finite number of possible switching states for a power converter, such as VSI. This control algorithm has the advantage of having no closed loop gains, depending only on the constituent elements of the system and the quality of the electrical model used. This allows the control system to have a good response to unpredictability of the loads that can be connected to the system. The equation used for voltage control is shown on this slide. Now the resultants obtained in simulation will be presented. First, the simulation results concerning the voltage controller VSI will be presented. In the figure presented, the electrical schematic used in simulation is presented. In this case, the VSI is generating the supply voltage for a set of loads, which consists of a linear load composed of three 50 ohm resistors with star connection and a nonlinear load, which is a diode bridge rectifier with RC load. The capacitor used is 500 microfarad and the resistance is 200 ohms. A passive filter is also used at the output of the converter, consisting of a 5 millihenry coil, a 30 microfarad capacitor, and a 2.2 ohm resistor. The rest of the parameters used in simulation are shown in the table. The first simulation result obtained is using PI control applied to VSI. The simulation starts with the linear load connected to the electrical system, and at 0.25 seconds the nonlinear load is added. With this simulation, it is intended to differentiate the behavior of the control algorithms in two different load situations, and also to verify their response in transient with the addition of the nonlinear load. It is found that with the linear load present in the control algorithm generates voltage with a THD of 1.18% on phase A, 1.14% on phase B and C. After the nonlinear load is added, these values become 1.27% on phase A, 1.23% on phase B and C. It can be seen that the presence of the nonlinear load slightly increases the THD values. In the transition response, there is a slightly peak in the currents consumed by the loads, but this does not affect the voltage produced by the VSI. These results were obtained using a kappa P of 130 and a kappa E of 5. The second result obtained in simulation is with PR control. The simulation was performed with the same characteristics as the simulation performed with the PI control, using two situations with different loads. These results in terms of THD for the linear load were 1.16% on phase A, 1.06% on phase B, and 1.09% on phase B. With the addition of the nonlinear load, the THD values became 1.25% on phase A, 1.16% on phase B, and 1.18% on phase C. As with the result obtained earlier, the addition of the nonlinear load caused the THD of the voltage to increase slightly. In transition response, there is a slight spike in the currents consumed by the load, smaller than the previous result, while still not affecting the voltage produced by the VSI. These results were obtained with a kappa P of 200 and a KS of 1000. At least the results obtained using the model predictive control algorithm are present. The simulation performed was exactly the same as for the control techniques presented previously. Thus, the voltage generated using the model predictive control with only the linear load presented in the system present a THD of 1.21% on phase A, 1.18% on phase B and C. With the addition of the nonlinear load to the system, the THD values increased slightly to 1.35% on phase A, 1.31% on phase B, and 1.30% on phase C. In the transition response, it can be seen that the peak in the current consumed by the loads is almost non-existent compared to the other control techniques. Having presented the simulation results obtained for the voltage control VSC, the results obtained for the current control VSI will be now presented. The figure shows the electrical schematic used in simulation. The simulation parameters are the same as those used in the simulation of the voltage control VSI and are presented in the table. Since the VSI is being current controlled, it is responsible for injecting power into a 3-phase 400 volts 50 Hz system. A passive filter is also used at the output of the converter, consisting of a 5 mA coil, a 30 microfarad capacitor, and a 2.2 ohm resistor. The first result obtained is using the PI control. In order to check the behavior of the control, two different reference values are used during the simulation. This reference current variation is quite common in systems such as solar variation or wind speed variation in renewable energy applications. First, the reference current is 25 amps, resulting in currents with THD of 2.31% phase A, 2.32 phase B, and 2.30 phase C. At 0.25 seconds, the reference current is increased to 50 amps. The results obtained in the THD of the currents decreased to 1.22 phase A, 1.23 phase B, and 1.21 phase C. In transition response of the PI control with increasing reference current, there is a peak in currents of 70 amps. These results were obtained using a KPP of 100 and a KPI of 50. The next result obtained is using the PR control. The simulation performed for this control technique is exactly the same as before, where there is a variation in the reference current provided to the control. First, the reference current is 25 amps, obtaining current with a GHD of 2.29 phase A, 2.32 phase B, and 2.27 phase C. At 0.25 seconds, the reference current is increasing to 50 amps. The results obtained in the THD of the currents decreased to 1.18% phase A, 1.20 phase B, and 1.17 phase C. In a transition response of the PR control with decreasing reference current, there is a peak in the currents of 9 amps, slightly lower than the value obtained with the PI control. These results were obtained with a KPP of 120 and a KPI of 800. Finally, the results obtained with the MP control are presented. First, with a reference current of 25 amps, currents are generated with a GHD of 1.81 phase A, 1.86 phase B, and 1.79% phase C. At 0.20 seconds, the reference current is increased to 50 amps. The results obtained in the THD of the currents decreased to 0.91% phase A, 0.96% phase B, and 0.91 phase C. In the transition response of the PR control with the increased reference current, it's verified that there is no peak current presenting a smoother behavior. With the results obtained in simulation, a comparison between the three algorithms was made. In voltage control, in terms of harmonic distortion, the results are very similar, with the PR control presenting the best result. Regarding the difficulty of implementation, the PI and PR control algorithms are very similar, with the MP being slightly more complex due to obtaining the system model. In current control, the implementation difficulty is the same as for the voltage control, since the algorithms are the same using current signals. In terms of THD, the MP control gives slightly better results. Furthermore, this algorithm does not cause current spikes, unlike PI and PR, The PI is one with the largest current spike of 17 amps. This paper compared the performance of three control algorithms for voltage source inverter. PI, PR, and model predictive control algorithms were applied for voltage control and current control. As demonstrated in simulation, all algorithms show good results in terms of THD. In voltage control, the PR control algorithm gives slightly better results in terms of THD. The implementation difficulty is similar for PI and PR control, being MP more difficult to implement. In current control, the PI and PR algorithms show very similar results, and since they have static gains, they cause an overcurrent transient in the current reference change because the error is too high at this instant. The MP algorithm shows better results with respect to the transient. It is also a lower THD in the current control. Nevertheless, it should be noted that this algorithm only works well with a good model of the electrical system, which depending on the code can be difficult to obtain. As future work is planned to validate experimentally the three control algorithms to have a better perception of their behavior in real application in comparison with the simulation results. Thanks for your attention.